Hi everyone, welcome to my another lecture on singularity. This is the third lecture on singularity. Earlier I had explained very nicely what is singularity and types of singularity. Types of singularity, that is isolated singularity, I have already explained. Now there are three types of isolated singularity. There are three types of isolated singularity. Okay. In this lecture, the learner will be able to understand the removable singularity. Removable singularity. Okay. What is removable singularity? How to solve a problem using removable singularity. These are the outcomes of this lecture. Okay. So let's start. So what is removable singularity? That means what is removable singularity? This is the third lecture. Okay. It means no negative power of z, all are removed. That is, if a function is given, if we expand this function, that is in power series expansion, then if that expansion doesn't contain any power of negative power of z, any negative power of z is not there, then we can say it is all are removed. Then it is called removable singularity. That means, that is, if all bi's are 0, all bi's are 0, no terms in principal part of z equal to 0, no terms in principal part, then z equal to z0 is removable singularity. If all bi's are 0, no terms in principal part. What is the principal part? Principal part of Lorentz series. That means if fz is given, if a function is given, if we expand this in power series expansion, then compare this with Lorentz series expansion. Lorentz series says that is fz. What is z? Z is a complex variable. That is n equal to 0 to infinity a summation a n z minus z0 whole to the power n equal to 1 to infinity bn z minus z0 whole to the power n. That means this is known as actually principal part. This is known as principal part. This is known as principal part. Okay. That means if the function is given, if we expand this in power series expansion, if after expanding, if there is no negative power of z, then we can say that is removable singularity. So we can prove a function is removable singularity by two ways: by expansion, series expansion, or by finding limit. That is, if another definition I am writing, if limit z tends to 0, fz dz fz, that is exist finitely, exist finitely, then z equal to z0, is called removable singularity. That means when a function is given, if we find the limit at z tends to z0, that is 0, fz exists finitely. That means the value of fz at limit z tends to 0, then it is called exists finitely, means finite value we will get, no infinite value. If we get finite value, then we can say it is removable singularity. That means if it means all negative power of z are all removed. This is very important. All are removed. That is no principal part. Then we can say it is removable singularity. For example, if we take say fz equal to sine z. if we expand sine z, then what we get? Sine z expansion. That is, if we expand this z minus, that is z cube by factorial 3, z cube by factorial 3 plus z to the power 5 by factorial 5 plus dot 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 dot. So this is, you see, in this expansion there is no negative power of z, no negative. So sine z is always, fz equal to sine z is always removable singularity, always removable, no negative power of z when sine z expanding in series expansion. Then we get this. That means we see that in this expansion there is no negative power of z. So sine z is known as removable singularity. Now I am taking some example. That is some example. Say I'm just removing this part. That is, I'm taking some example of removable singularity. Taking some example. One example is, suppose limit z, suppose fz equal to example 1, fz is equal to sine z by z. You see, sine z by z, z not equal to 0 is removable singularity. Show that. So removable singularity. Removable show that. Okay, show that. So that fz equal to sine z by z, comma z not equal to 0 is removable singularity. So now I am finding limit z tends to 0, that is sine z by z. This again can be written as limit z tends to 0, sine z by z, that is sine z by z, that is 0 by 0, 0 by 0. You see, if we put z equal to 0, so 0 by 0, then apply a L'Hospital rule, that is differentiating numerator and denominator. Denominator differentiation 1, numerator differentiation is cos z. Okay, now put z equal to 0, we are getting this is 1, that is finite value. Understand how to find this limit? How to find this limit? Understand? Because that is, if we put z equal to 0, then sine 0 is 0, here is 0, so 0 by 0 form. That is 0 by 0 form here. 0 by 0 form. That is 0 by 0 form. When 0 by 0 form is there, then what will you do? You have to differentiate numerator and denominator separately. So now sine z differentiation is cos z, z differentiation is 1. So this is finite value. So it is finite value. Understand? So finite value. So that is by second definition. If it is finite value, we can say therefore fz that is we can say that is fz equal to sine by z by z. That is therefore fz is removable singularity. Removable singularity. Okay. Otherwise, you can do another way. Otherwise, देखो, sine z by z. This is fz is equal to sine z cube z minus z cube by factorial 3 plus z to the power 5 by factorial 5 plus dot 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 dot. Okay, minus. Okay, now by z. Now if we take, that is z common from numerator, then 1 minus z square by factorial 3 plus z to the power 4 by factorial 5 minus dot 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 dot. So you see, in this expansion there is no negative power of z. No negative power of z. So there is in this expansion no negative power of z. No negative power of z. That means if we compare this with Lorentz series, that means in Lorentz series, you see the principal part becomes 0. That is B1, B2, B3 all are 0. So no negative power of z. Only this part, that is this part only given. So it is known as removable singularity. Therefore, Fz you can say, therefore Fz is removable singularity. Okay, there is no negative power of z in this expansion, so therefore we can say Fz is removable singularity, removable singularity. Okay, so this sum we have done, that is two methods. That is, one method is by limiting method, and another method is by series expansion method. If we expand sin z this, so this way you can do. Okay, so that is no negative power of z on, this is the main part. Actually, if we expand this, if the given function, that is fz, then if we get no negative power of z, then we can say it is removable. We can say it is removable. Okay. Now second sum I am taking. Example number 2. I am taking example number 2. Okay. Example number 2. Example 2 says that, example 2, I am taking, this is from question paper sum. I am taking all our question paper sum. Okay. That is example 2. Show that fz is equal to e to the power z minus 1 by z, z not equal to 0, has removable singularity. Has removable singularity. Okay. So what is the solution? So by two ways we can find limit. You have to find limit z tends to 0, e to the power z minus 1 by z. So this is the method, that is if we by L'Hospital rule, if we put z equal to 0, then 1 minus 1 by, that is 1 minus 1, 0 by 0. This is 0 by 0 form. 0 by 0 form. The by L'Hospital rules, L'Hospital's by L'Hospital rules, we get, what is this? Limit z tends to 0. You have to differentiate numerator and denominator with respect to z. So e to the power z minus, this is 0 by, this is 1. If we put z tends to 0 now, it is not coming 0 by 0. So you can put the limit. So that is e to the power 0. Answer is 1. That is finite value. Finite value. Finite value. Finite value. We are getting the finite value. Okay. We are getting finite value. So we can say, therefore fz is equal to e to the power z minus 1 by z, z not equal to 0, as removable singularity. This is one process. Now by series expansion you can do, by series expansion, that is fz equal to, you see, otherwise method. Fz equal to e to the power z minus 1 by z. That means 1 by z I am taking here. So e to the power z formula is 1 plus z plus z square by factorial 2 plus z cube by factorial 3 plus z to the power 4 by factorial 4 plus dot then minus 1. So minus 1 this. So this and this getting cancelled. Now 1 by z into this, that means we are getting 1 plus z by factorial 2. Try to understand. Plus 1 by z into this, that is z square by factorial 3. 1 by z into this, that is z cube by factorial 4 plus dot. Try to understand. Here you see there is no negative power of z. That means we expand we expand binomially, that fz is becomes the result this. So in this expansion, you see there is no negative power of z, no possibility, no negative power of z. So we can say all negative power of z are removed. That means we can say fz equal to e to the power z minus 1 by z is removable singularity. This is second sum. I'm taking sum number 3. Okay, I think everybody understood very nicely. If you have any doubts, any clarification, then you can contact me with this phone number. This is phone number. This is my WhatsApp number also, I am saying. Okay, now I'm checking. That is what we have learned from here. For removable singularity, we can do by expansion of series or by limit method, by finding the limit method. Two ways we can do. Okay, be careful. Removable singularity. So that other sum, example number 3 I am taking here. Show that if z is equal to cosec z minus 1 by z has singularity at z equal to 0 and is removable singularity. First we have to say it has a singularity at z equal to 0. Secondly, we have to see it is removable singularity. Because we know that is isolated singularity are of 3 types. That is, one is removable, then pole, then essential singularity. First removable, then pole, then essential singularity. Okay, so we are doing today that is only removable singularity, so that it has a singularity at z equal to 0. Now if we expand this, that is cosec z can be written as 1 by sine z. So if we take LCM, that is z into sine z. So here z minus sine z. Okay, to get singularity, that is then denominator equal to 0. That is, if we put denominator equal to 0, then z equal to 0 we are getting. That is, if we put suppose z into sine z is equal to 0, therefore we can say z equal to 0. So z equal to 0, or if sine z 0 means again z equal to 0. Sine z 0 means sine 0 0, so z equal to 0. So z equal to 0 has a singular point. That is, it has a singular point. Z at z equal to 0. How to get the singular point? We have to put the denominator portion is equal to 0. That means fz is not defined when z into sine z is equal to 0. So that is, this is the procedure to get the singular point. That is, z equal to 0 is. Now that is removable singularity. Okay. Now